Let's now discuss how we would go about restricting a domain so that a function that is not one-to-one can become one-to-one, and thus the inverse function would exist. So the domain of a function can be restricted so each y value is unique. We saw in the first section that quadratics fail the horizontal line test, which means the inverse function does not exist. So f of x here is equal to x squared for all real values of x. So the domain is not restricted. So this function does not have an inverse function since it fails the horizontal line test. But what would happen if we cut the parabola in half here and got rid of one of these halves? It would no longer fail this horizontal line test. So if we look at the points for f of x, we see that the y values are not unique. We have positive 4 for two different inputs, positive 1 for two different inputs. But here at 0, this is where our line of symmetry is. So if we were to eliminate the points that were smaller than 0, and we restrict the domain to x is greater than or equal to 0, then we would have unique y values of 0, 1, and 4. Or if we eliminate these points, then our domain could be x is less than or equal to 0. And now that domain would have unique y values 0, 1, and 4. So for parabolas, we are going to find the point of symmetry and restrict the domain so that we wind up with unique y values. So that is the point of restricting domains. Now, one more thing I'd like to point out. We'll know if we restricted the domain at the line of symmetry by checking numbers that are equidistant from that line of symmetry. So for example, 0 here represents that line of symmetry for f of x. So we'll know if we restricted the domain correctly. If we plug in -1 for x, that will give us an output of 1. And if we check a number equidistant from 0 in the opposite direction, so we went down 1, so we want to go up 1, and that also produces an output of 1. And this makes sense because if we go in equal distance in the negative direction and in the positive direction along the x-axis, the y values for those points along the curve will be equal. So this is how we will go about determining if we restricted the domain in the correct place. We'll test values at equal distances away from that line of symmetry to make sure that their y values are equal. So let's take a look at this process a bit further. We have f of x is equal to x squared for x is greater than or equal to 0. So normally our x squared is a parabola, but since we restrict it here with x is greater than or equal to 0, now we have the portion of the function that could pass the horizontal line test. And since it passes the horizontal line test, now the inverse of f of x exists. This is why we want to restrict domains, so that we can take a function that normally would not have an inverse, and now it does have an inverse. Now for quadratic functions with a single variable, the domain can be restricted along the x-axis at a to make the function one-to-one. So if the function is given in vertex form, the variable will appear once, so you'll get a single variable, and it'll be in the form f of x is equal to x minus a squared for x is greater than or equal to a, or x is less than or equal to a, depending on if we're eliminating the values above a certain point or the values below a certain point. That line of symmetry is a. And by doing this, the inverse function will pass the vertical line test. So let's take a look at this. Let's say we were given f of x is equal to 2 times x minus a squared plus 1. This is what that parabola would look like. x minus a represents a shift to the right, and our line of symmetry will be at point A along the x-axis. If x is a, that gives us a minus a is equal to 0. Whatever value we can set x to, that would allow the expression inside of the parentheses equal to 0. That's the value along the x-axis where the line of symmetry exists. A couple things to notice when a function is in vertex form. The coefficient outside of the parentheses and the constant will not affect the domain. So this +1 shifts the function up 1 along the y-axis. So this point here is at 1, since this shifted up 1. And the coefficient affects the width of the parabola. But the line of symmetry does not change. So that is why the coefficient and this shift from the constant do not affect our domain. So keep that in mind. So let's say we eliminated the values above a along the x-axis and we restricted the domain to x's less than or equal to a. This would be the result. And as a result of restricting the domain at a, we can now reflect this function across the line y is equal to x. And we see the inverse function exist, and it can now pass the vertical line test since the domain was restricted for f of x. Let's take a look what happens if we restrict the domain above a, so x is greater than or equal to a. If we reflect this across the y is equal to x line, this would be our inverse function. And this function can pass the vertical line test as well. So this is what happens when we shift the parabola to the right, when we have x minus a. What happens if we shift the parabola to the left? For f of x is equal to x plus a squared, for x is greater than or equal to negative a, or x is less than or equal to negative a, this will result in the inverse function passing the vertical line test. Let's say we were given f of x is equal to 2 times x plus a squared. This is what that parabola would look like. The line of symmetry is going to be at negative a. Inside the parentheses here, we have x plus a. So x would be negative a, making the expression inside of the parentheses 0. So that is where our line of symmetry is, negative a. So let's say we restricted the domain for x's less than or equal to negative a. This would be the result. And if we reflect this across the y is equal to x line, this is what the inverse function would look like. And since we've restricted the domain for f of x up here, the inverse function can now pass the vertical line test, making it a function. Now let's say we restricted the domain for x is greater than or equal to negative a. So now this would be what f of x looks like. And now if we reflect this across the y is equal to x line, this is what the graph of the inverse function would look like. And since we restricted the domain for f of x up here, f inverse of x can now pass the vertical line test, making it a function. So that is how domain restrictions lead to inverse functions existing. And this is how we go about restricting domains. But let's go ahead and walk through an example together. You'll be asked to restrict the domain of a function so it is 1 to 1 and check the answer. And we're given f of x is equal to 3 times x minus 5 squared minus 1. So how would we restrict the domain for this function? Step 1, we want to set the expression inside of the parentheses equal to 0. So we have x minus 5 is equal to 0. And now step 2, we want to solve for x. So we do so by adding 5 to both sides, showing us that x is equal to 0 plus 5, which is 5. So this is where our line of symmetry is. Along the x-axis, it's at positive 5. So we can restrict the domain by setting the domain to less than or equal to 5, or by setting x to greater than or equal to 5. So this would be our answer. We want to restrict the domain for x is less than or equal to 5 or x is greater than or equal to 5. Now, how do we go about checking the answer? We want to check the answer by plugging in two numbers equidistant from 5. This will show that the y values were the same at different x's. This is the line of symmetry. If we go one below to 4 or one above to 6, they should have the same exact y values because the parabola is going up at an equal rate on both sides of the line of symmetry. So whatever you get for your answer, you want to plug in the number right below your answer and the number right above your answer. So when we plug in 4 for x, we get f of 4 is equal to 3 times 4 minus 5, which would be negative 1, squared minus 1. Negative 1 squared is 1. 3 times 1 is 3. And 3 minus 1 is equal to 2. So where x is 4, the y value of the function is 2. So this is the line of symmetry. If when we plug in 6, we get 2 as well. So f of 6 is equal to 3 times 6 minus 5. 6 minus 5 would be 1. 1 squared is 1. So 3 times 1 is 3. And 3 minus 1 is 2. So f of 4 was equal to 2. And f of 6 is equal to 2. Letting us know that 5 was the line of symmetry. So we can restrict the domain for this function for x is less than or equal to 5 or x is greater than or equal to 5. So that is how we go about restricting the domain when our function is in vertex form. Let's now have you complete a few practice questions. Restrict the domain of the function so it is 1 to 1 and check the answer. Question number 1. F of x is equal to negative 2 times x minus 3 squared plus 4. Question number 2. G of x is equal to 3 times negative x plus 2 squared minus 1. In question number 3, h of x is equal to negative 1 times negative 4 plus x squared plus 3. Pause the video, answer these questions, and then press play when you are ready to begin. Question number 1. We are given the function f of x is equal to negative 2 times x minus 3 squared plus 4. Step 1, set the expression inside of the parentheses equal to 0. So that gives us x minus 3 is equal to 0. And now step 2, we want to solve for x. So we do so by adding 3 to both sides, showing us x is equal to 0 plus 3, which is 3. So our line of symmetry for the parabola is where x is equal to 3. So step 3, set x to less than or equal to 3. And step 4, set x to greater than or equal to 3. And this would be our answer. We can restrict the domain to x is less than or equal to 3 or x is greater than or equal to 3. And now, step 5, we can check the answer by plugging in two numbers equidistant from 3. This will show that 3 was in the middle, or the line of symmetry. So f of 2 is equal to negative 2 times 2 minus 3 squared plus 4. 2 minus 3 is negative 1. Negative 1 squared is 1. So negative 2 times 1 is negative 2. And negative 2 plus 4 is positive 2. So we get f of 2 is equal to 2. So when we plug in 4 for x, we're looking for the function to have the same value, positive 2. When we plug in 4 for x, we get negative 2 times 4 minus 3 squared plus 4. 4 minus 3 is 1. 1 squared is 1. So we get negative 2 times 1, which is negative 2. and negative 2 plus 4 is positive 2. And since f of 2 and f of 4 produce the same output, that lets us know that the answer to question number 1 is the domain can be restricted at x is less than or equal to 3 or x is greater than or equal to 3. So that is the answer to question number 1. Let's now have a look at question number 2. We are given the function g of x is equal to 3 times negative x plus 2 squared minus 1. So step 1, set the expression inside of the parentheses equal to 0. So that gives us negative x plus 2 is equal to 0. And now step 2, we want to solve for x. So we begin by subtracting 2 from both sides, showing us negative x is equal to 0 minus 2, which is negative 2. And to get rid of this coefficient of negative 1, we divide both sides by negative 1, giving us x is equal to negative 2 divided by negative 1 is positive 2. So we get x is equal to 2. So this is where the symmetry for the parabola lies. So we want to restrict the domain here. So step 3, we want to set x to less than or equal to 2. And step 4, we want to set x to greater than or equal to 2. So we restrict the domain for g of x to x is less than or equal to 2 or x is greater than or equal to 2. And now step 5, we check the answer by plugging in two numbers equidistant from 2. So we'll plug in 1 and we'll plug in 3 to see if they produce the same output value for the function g. So g of 1 is equal to 3 times negative 1 times 1, which is negative 1. Negative 1 plus 2 is positive 1. 1 squared is 1, giving us 3 times 1, which is 3. And 3 minus 1 is equal to 2. So g of 1 is equal to 2. So when we test g of 3, we are looking for the output value to be 2 as well. So g of 3 is equal to 3 times negative 1 times 3 plus 2 squared minus 1. Negative 3 plus 2 is negative 1. Negative 1 squared is 1. 3 times 1 is 3. And 3 minus 1 is 2. So since g of 1 and g of 3 produce the same output value, that confirms that the answer to question number 2 is x is less than or equal to 2 or x is greater than or equal to 2. So that is the answer to question number 2. Let's now have a look at question number 3. We're given the function h of x is equal to negative 1 times negative 4 plus x squared plus 3. So step 1, set the expression inside of the parentheses equal to 0. That gives us negative 4 plus x is equal to 0. And now step 2, solve for x. So we'll do so by adding 4 to both sides, showing us x is equal to 0 plus 4, which is 4. So this is where the line of symmetry exists for the parabola. So step 3, we want to set x to less than or equal to 4. And step 4, we want to set x to greater than or equal to 4. So the answer for question number 3 is x is less than or equal to 4 or x is greater than or equal to 4. And we can check the answer by plugging in two numbers equidistant from 4. So we'll plug in x is 3 and we'll plug in x is 5. H of 3 is equal to negative 1 times negative 4 plus 3 squared plus 3. Negative 4 plus 3 is negative 1. Negative 1 squared is 1. Negative 1 times 1 is negative 1. Negative 1 plus 3 is positive 2. So h of 3 is equal to 2. So when we plug in 5 for x, we want h of 5 to equal 2 as well. H of 5 is equal to negative 1 times negative 4 plus 5 squared plus 3. Negative 4 plus 5 is positive 1. Positive 1 squared is 1. Negative 1 times 1 is negative 1. Negative 1 plus 3 is 2. confirming h of 3 and h of 5 have the same output value, confirming the answer to question number 3 is x is less than or equal to 4, or x is greater than or equal to 4.